Hello and welcome to anyone joining. Thank you for being here. Go ahead and get yourself ready with a notebook, grab a pencil or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today, here we have some physics with calculus. So if you're in Calculus 2 or AP Calc BC, you might remember that some problems in Calculus 1 involve particle motion, position, displacement, velocity, acceleration, speed, all that jazz. This is going to come back again in Calc 2 or Calc BC in the form of linear motion, differential equations, even parametric equations. So you'll see that later on. But for now, we're focusing on a problem from physics, pretty simple to understand problem of what's going on, at least physically speaking. We have a model rocket that is fired vertically upward with an initial velocity of 49 meters per second from a tower 150 meters high. So this problem would take a little while. There are a lot of parts to it. I would say give yourself about 12 to 15 minutes. Should be a decent amount of time. Pause the video, see if you can figure it out for yourself first. And then when you're ready, unpause the video, come on back. See how we do this here. So with these physics problems, one of the best things to do is draw a diagram. So I'm just going to draw a basic cliff-looking thing. This is 150 meters, the height from which the rocket's being launched. It's going upwards, but we presume that it's going to go down after it reaches its highest point. And we have a velocity, a starting velocity, which is a positive 49 meters per second. Okay, so that's regardless of what parts of the question I'm answering. That's just true for this entire situation. It's going to hit the ground at some point. It's going to reach a highest point, So the question is, how do we answer these questions? That is, the best thing to do, the best strategy to use for these questions, first of all, is to identify which moment in time they are referring to, then determine the desired quantity. If you can follow those two simple principles, it's going to be really easy because you can get overwhelmed. Sometimes they're asking about velocity, but they're mentioning the maximum height, and sometimes they're asking how long, but they're mentioning maximum height. Sometimes they're saying how fast when it hits the ground, how long till it hits the ground, all of these different questions. You need to know how to interpret those. So these 6 parts are going to allow us to interpret some of these questions. How long will it take? That seems like that's what they're asking for. How long will it take? They're basically asking for t. But we need to know when they're talking about this. How long will what take? How long will it take for the rocket to reach its maximum height? So this tells us something important. The fact that it reaches its maximum height tells us that the velocity equals 0. We can use that fact to now find a time, and that'll be our answer. Okay? But I do also want to address a few things. In physics, when we have free fall motion, or anything falling, anything that has been thrown in the air and it's only under the influence of gravity now, it'll always follow this equation, Vf equals V initial plus A times T. Now, if you're in physics, you already know this formula. It's a kinematics formula. And it basically says that the velocity after some time is the starting velocity. In calculus, we call this the initial condition, but it's basically just the starting velocity. And then this is the overall change in velocity. But since it's like the increase or decrease in the velocity based on the acceleration over time. But this change in v is essentially the integral of a dt. So now that we're in calculus, we use integrals to describe that total change. I guess I should call it the net or overall change in v. Okay, so that formula is true when we have a constant acceleration. And another formula that's useful is at the final position. Sometimes we even used to use a quadratic function in Algebra 2, pre-calculus, other levels of math, where we had free fall situations. We would use y equals, the final position is equals to 1/2 a t squared. Usually a stands for the acceleration due to gravity, plus v0 times t, that's the initial velocity times t, plus the initial position. So this formula is what we're going to use pretty much every single time, but this formula is a result of taking the integral. So if you're confused about why I brought this up, what I'm saying here is that every time you take an integral of the acceleration, you're going to get the velocity. And then when you take an integral of the velocity, which is going to be integral of at plus the initial velocity, then we're going to end up with 1/2 at squared plus the initial velocity times t plus a constant, which is the initial condition of position. You understand now? So I'm saying that if we take the integral of acceleration and then the integral of velocity, we get these formulas here. It's sort of where these formulas come from. This is called the kinematic chain in physics. So I'm not going to do the shortcuts, I'm going to do the long way, but I just want you to know that there is a shortcut, basically, that you can use these formulas directly whenever you have a free fall situation. Okay, let's go back to here. How long will it take for the rocket to reach its maximum height? Which means v equals 0. Well, first of all, we know that a, since we're in meters, a is equal to negative 9.8. And so we're going to take an integral from 0 to t. We don't know what the time is at the end of this situation. We don't know when it reaches its maximum height. That's actually what we're looking for. But we know that the integral from 0 to t of the acceleration is simply v of t minus v0, where v0 is the initial velocity. So this is going to be the integral of negative 9.8, and this is from 0 to t. And that's simply negative 9.8t if you work out that definite integral. But if we add the v0 on both sides, so we're going to add 49 to both sides, now we have that this is equals to v of t. All right, we're in great shape now. So there's our velocity. We want to set it equal to 0. Why do we want the velocity equal to 0? Let's remind ourselves again. It's because at the maximum height, the velocity is 0. So if I set the velocity equal to 0 and then solve for time, it will tell me the amount of time to have 0 velocity. In other words, the amount of time to reach that maximum height. Okay, so we're going to end up with 49 equals 9.8 t. They made this pretty nice. T simply equals 5, and this would be in seconds. So that's how long it takes for the velocity to become 0. If we look at our diagram, that means that this point up here is located at t equals 5. I don't know the height, I just know that it happens 5 seconds after it's been thrown. Okay, let's move on to part B. What is the maximum height? So our condition, or rather our useful information that we already know for this, our moment in time, if you will, is t equals 5 seconds. Okay, but I need to find out what the maximum height is. What's the height at 5 seconds? So really, I'm looking for x of 5. And if we use this shortcut, we could just plug in 5 for the time. We could plug in 150 for the height. So this time would be 5. We plug in our a value, that would just be negative 9.8, so 1/2 of that's, negative 4.9. And then we would plug in the initial value, the initial velocity, which is 49. If we plug all of that in, we will just get the final position. You would have done this like in Algebra 2 when you were solving this type of problem. But since we're big boys and girls in calculus now, we're going to take a look at the integral. So to get x5, I will realize that the integral from 0 to 5 of v is equal to x of 5 minus x of 0. And x of 0, which is the initial position, is 150. So let's make some space here. We know that the velocity function is negative 9.8 t plus 49. So this is going to be equals to negative 4.9 t squared, that's half of negative 9.8, plus 49t. Do you see how it's becoming the exact equation that we had over here? 1/2 at squared plus v initial times t. That's exactly what we have here. And this is going to be evaluated from 0 to 5. But remember, this is equals to x of 5, that's what we're after, minus the original position of 150. So we have to add 150 to whatever we get when we plug in 5. Isn't that exactly what I said we were going to be doing? We're essentially just plugging in those initial conditions of the height and the starting velocity, half of the acceleration, which is basically half of the acceleration due to gravity, and then we're plugging in 5 for the time to get our final position. So let's see, this is going to be 25 times negative 4.9. Didn't really prepare for this. 490, so that's going to be 1 rusty. 22.5? Something like that. Plus 49 times 5, which should just be half of that, 245. Double of that. What am I saying? 245. And then we add 150 to it, so we get 122.5 plus 150, which, if you notice, I'm going to take it one more step. This here is 122.5. That's how much higher than the 150 we got. So if you wanted to know how high off the platform it went, that's how high it went from the platform. But its maximum height is however high it went off the platform plus the starting height of the platform. So this would be 272.5 meters. So if someone were just on the ground, not on the platform, and they saw this rocket get launched, where's the diagram? Like if someone was on the ground here, hello, they would see this being 272.5 meters up. Okay, let's continue. How long will it take for the rocket to pass its starting point on the way down? Again, how long will it take? But for this one, to pass its starting point, we're going to exploit the symmetry of a parabola and the symmetry of an equation such as this. How long will it take for it to pass the starting point? Let's mark that location. It's going to go up, and it's going to come back down. So this is back at the starting height. Because of the symmetry of this parabola, it's going to take 5 seconds to go up, which means it's going to take 5 seconds to get back down to where it started. That is pretty easy there. Now, the other way to solve this, if we're trying to use just pure calculus and not just visual analysis, is we would take this expression, the integral of vt, we would say the integral from 0 to t of vt, which we know is negative 4.9 t squared plus 49t. We would say that this is equals to 0. because we want the displacement to be 0. If we said x of t minus x of 0, we want the position to be the same. We want it to be at the starting point, the starting height. So these would be equal. And when we set that equal to 0, we can simply factor 4.9t, negative 4.9t that is, and end up with t minus 10. So you see that t equals 10 is certainly a solution to that. This would be in seconds, by the way. That's not 105, that's 10 seconds. In fact, maybe I'll put... I'm Mexican, so it just looked like los. It just looked like LOS. 10 seconds. Okay, another pretty easy question to answer that doesn't really technically require calculus. What is the velocity when it passes the starting point on the way down? Any guesses? It's going 49 meters per second on the way up as soon as it's launched. Once it comes down to the same height, it's still going to be 49 meters per second. So passes the starting point, but we want to know what is the velocity. Okay, so it's going to be the same exact speed, except it's going downwards instead of going upwards. And that kind of just makes sense, that on the way back down, it has pretty much the same velocity. That's true in reality, with the exception of things like, air resistance slightly affecting the motion of objects, but for the most part, should have the exact same velocity coming down. Yeah, like I said, unless there's like a bunch of wind or something. So we're going to say negative 49 meters per second. Now, if we wanted to solve that, we could just plug it into the v of t equation. We already have an equation for v of t. We would plug in the time that we just got, and we would have negative 9.8 times 10 plus 49, and that also gives us negative 49. So you can do it by plugging it into the function for v, using integrals, using calculus, or you can just sort of logic this one and again exploit the symmetry of the motion of this object. Okay, part E. Oops. How long will it take? So we're looking for time. And what do we want to happen? The rocket to hit the ground. That means that the position, x of t, equals 0. So we want x of t to equal 0. Well, let's go back to our expression, the integral from 0 to t of v of t. So in this case, we want the position to be 0, not the change in position to be 0. For part C, we had the change of the position be 0, because x of t and x of 0, these are both 150, which is 0. It's the starting height, and that's the height at this point when it passes it on the way down. It should have the same height. So here, we're going to say that this is negative 4.9. We kind of get the drill. We've already done the antiderivative of v of t, so I'm just going to write it out. From 0 to t, which is just going to be as it's written right now. It's not going to change. If I plug in t, you get the same thing. If you plug in 0, you get 0. But this needs to be x of t minus 150, and we're setting x of t equal to 0. So that means we're solving the equation negative 4.9 t squared plus 49t plus 150, that's the position function. We're setting this equal to 0. So we're essentially just solving a quadratic equation. You know how that's never going to go out of style. Maybe this thing factors, but I kind of doubt it. So let's just use the quadratic formula carefully. You can probably use a calculator for this. I think it'll take too long for you to work it out by hand. Negative 4.9, 150 over 2 times negative 4.9. Notice that 9.8 kind of comes back, even though we got rid of it at some point, since we have 2 times 4.9. Now it's negative 9.8. Okay, so those are our possible values for t. Let's try to figure out what that is. 49 squared is 2401, and this is going to become plus Let's see, 19.6, 29.4. Yeah, 29.40. Yikes. Getting a little bit lost in the sauce with these numbers. These are not the nicest numbers. So we have negative 49. You could just work this out with the calculator. You can skip all this if we want to, but I have to figure it out. So 53.41, which is like not that great, but it's in between, I guess, 72 and 73. It's a little bit closer to 73. Let's see, 50.41, 51.28, 53.29. Oh, actually, it's really close to 73. Yeah, it's really close to that. Let's see, negative 9.8. So, do we want the plus or the minus? It's always a trick question there, isn't it? We want the minus. So I'm just going to call it 73. It's really close to 73. Over negative 9.8. We want the minus, because if we do the plus, we're going to get a positive on top divided by a negative. That is not valid. So we're going to go with negative 122 over negative 9.8. So it's like about, if I had to guess, 12.2. I mean, that's just kind of a rough guess, but let's say 12.3-ish. You can use a calculator for sure and see what it comes out to be. So 12.3-ish is the time. And is this reasonable? Well, yeah, kind of, because it should definitely be more than 10 seconds. 10 seconds is how long it takes to get to the starting height. And remember, it's going really dang fast at that point, and gravity's helping it. So that last 150 meters, it probably clears it like really quickly, honestly. Okay, yes, and then the final thing to ask about it, what will be its speed at impact? So we're asked for the speed when it says at impact. That's not necessarily explicit. We have to figure out what that is implying. That is implying that x of t equals 0, meaning we can use the time that we just found. So maybe I should put this in a calculator just to get an accurate value. Otherwise, my speed's going to be off, and then what good am I if I'm just giving you wrong answers at that point? 22, 9.8. Okay, 12.45. So I mean, I'd even be cool with like 12.5. That's probably more accurate than 12.3. So when t equals 12.5, what is the speed? Well, speed is just velocity with no direction. Like, it's how fast you're going, regardless of which direction you're moving in. So we can just use v of 12.5 and then put it in an absolute value. And this is essentially going to be the absolute value of negative 9.8 times 12.5 plus 49. Okay, so we're going to get, I should probably put that here. Let's see, 9.8, 12. Is it really? 122.5. Yeah, it's 122.5. That's funny. Oh, but it's negative. And then we have plus 49, so we're basically just subtracting those. So we're going to get the absolute value of negative 73.5 or 73.5. And this is going to be in meters per second. It is going downwards, but we don't really care about the direction when we're answering a question about the speed. Okay, so very fast indeed. All right, that's a little bit of an investigation on how to use some of these cues, the way that they phrase the question, to pinpoint a moment in time, and then you can determine the desired quantity. You might need to use an integral or an antiderivative, but you could also keep these formulas in mind. These are some very useful kinematics formulas that are essentially coming right out of the calculus that we're doing anyways. Okay, I think that's enough blab out of me. I'll see you guys next time.